Hello, everybody, and welcome to the virtual seminar series on Bayesian decision-making and uncertainty. This is a rename of the previous virtual seminar series on
Hello,
Gaussian
everybody,
processes,
and welcome to the
spatiotemporal
virtual
modeling,
seminar series.
and decision-making systems. Or excuse me. This is a rename of the previous virtual seminar series on Gaussian processes, spatiotemporal modeling, and decision-making systems. We have a new and shortened name so that we're easier to find, but we still have the same web URL, which is gp-seminar-series.github.io. And we're really excited to have everybody here. Thank you for joining us. My name's Alex. I'm an assistant research professor at Cornell and one of the organizers who's going to be hosting today's event. I'd like to thank my fellow organizers, Z Wang, Natalie Mouse, and Renato Berlingeri for all their work and helping put the seminar series together. And before we begin, I'd just like to make a short set of organizational announcements. Uh, First of those is following the seminar, we've got an amazing lineup of speakers for the coming weeks. You can find that on our website, which, to say it again, is gp-seminar-series.github.io. And you can see the schedule there. If you're listening on YouTube, you can also sign up to receive our mailing list with the Zoom invites, or you could just watch on YouTube. There's a Google group to register for to receive those emails with all the instructions on the website. Seminars take place at 1600 UTC, which is Coordinated Universal Time, and you should be aware that your local time zone may change due to daylight savings, so be on the lookout for that. If you're joining us via Zoom, you can use the raise your hand option to ask questions, or you can type your questions into the chat, and the speaker can choose to either pause and answer the questions during the talk, or they can hold the questions to the end, depending on their preferences. And with all of these announcements said, and thanks for bearing with me, they're a little bit long because it's the first one. It's my great pleasure to introduce Peter Frazier, who's a professor at Cornell, who will give today's seminar. And the title for that is Black Box Optimization for Humans with Unknown Preferences. Peter, take it away.
Awesome. Thanks, Alex. It's great to be able to be here. I'm excited to be able to kick off this seminar series. I was looking at the webpage and the organizers have put together a really awesome set of talks. So I'm looking forward to checking those out. I hope to be able to tell you something interesting today about the work that we're doing on Bayesian optimization for humans with unknown preferences. And this is joint work with Eitan Bakshi and Jerry Lin at Meta, Raul Estudillo, who's a postdoc at Caltech, currently on the job market, and Bhavik Shah at Stanford. So many of you in the audience probably are familiar with Bayesian optimization. So if you have a time-consuming objective function, then Bayesian optimization can optimize it. Let me just get everybody on the same page and explain a little bit about how that works. Imagine that I have an objective function shown in green here, dashed green line, and I've evaluated it at a few locations shown with these green dots. This is a function of just for simplicity, a one-dimensional variable x. And I've fit Gaussian process regression to it in this example. One could also use a variety of other Bayesian machine learning models. And Gaussian process regression shows to me an estimate of the function shown in the blue line, as well as some estimates of uncertainties shown via the shaded region. From that Bayesian posterior distribution on the objective function, I'm able to quantify the value of performing one more experiment towards the goal of finding a global optimum of this objective function. And that quantity, that quantification called an acquisition function, is shown below in this panel, again, versus the one-dimensional decision variable x and its value. And the idea in Bayesian optimization is that the point here in this figure, 0.7, that maximizes the acquisition function, that's the experiment to run that's most valuable, the point at which we should be evaluating f in order to make the most progress towards finding an optimum. We would take that recommendation, we would update our Bayesian posterior distribution on the objective function to incorporate that and recompute our acquisition function. Right. And if we do this a couple of times, many of you have direct experience using these kinds of algorithms, and we're likely to find a good solution with a small number of evaluations of the objective function. And this has had a fantastic amount of impact. One way that it's had an impact is that there are many tech companies that use Bayesian optimization to optimize machine learning hyperparameters, for example, the learning rate in deep neural networks. Optimizing model hyperparameters is something where if you want to evaluate the quality of a set of hyperparameters, it takes a significant amount of time because you have to, train and test a big neural network, and you don't get derivative information from your evaluations, preventing the use of methods like, stochastic gradient descent, and pushing us towards these kinds of methods like Bayesian optimization that assume black box objective functions without any gradient observations, and that assume that this black box is time consuming to evaluate. Right? So it's good at this kind of application where we pass in ML model hyperparameters X into a black box and get some measure of performance. It's also good at improving systems like, for example, that Meta operates, such as Instagram, where the way we evaluate the quality of a particular product change is through A/B testing, right? So in these kinds of settings, we have a product that's deployed online that relies on algorithms. These algorithms take a collection of parameters, parameter vector X, and we can assess the quality of changing the performance of a parameter vector by running an A/B experiment. A/B experiments typically take a long time, maybe at least 1 week, and don't provide derivative information on how the objective function changes as you change X. And so again, Bayesian optimization and other black box methods for time consuming to evaluate objective functions become attractive for these kinds of applications. The challenge that I want to talk to you about today is that often we don't know what the objective function is. Let me give you 2 examples where this happens. So first, if the machine learning model or the AI based model that you're training is a generative AI system that produces some content consumed by humans, it isn't always easy to assess the quality of that generated content. Right. So imagine, and I'm going to give an example later, but imagine that, I provide a prompt, which is an armchair in the shape of an avocado, and I want the generated image to be of high quality as assessed by a human. There isn't a simple to explain function that I can apply to the pixels in this image that gives me the quality of this particular response to that prompt. Another challenge that comes out a lot of the applied work that I've done at Uber is when tuning a system through A/B testing, often what is produced is not just a single number, which is the objective function value, but what you actually get is a panel of metrics. So for example, at Uber, if you're using Bayesian optimization to tune the parameters inside of an algorithm that's choosing matching decisions, so which driver a rider should get matched to when they make a request, the result of an A/B test will be a collection of, let's say, between 5 and 20 metrics that describe different ways that change impacts the business. So in this example, the change that was made reduced ETA by 5 seconds compared to the baseline set of parameters that are deployed in the market as a whole. Increased spinner time, so that's the amount of time that you wait on the screen before you're matched by a driver, by 3 seconds. So the 5 seconds was an improvement on ETA, but the change in spinner time was a degradation, right? So how do they trade off against each other? Revenue went up, but profit went down while driver earnings went up. Is that a good change or a bad change? It's not clear, right? So this is a second setting where what we want to optimize for is the business value implied by a panel of metrics, but it isn't clear how to compute that business value. It's hard to find a specific, mathematical function that you can write down that gives that number to you. So how have people tried to tackle this problem in the past? So one is specify a utility function, right? So we might have conversations with business leaders in the panel of metrics setting where we come up with weights on these different metrics. And then we would use Bayesian optimization to maximize the resulting utility function that we get by taking this weighted combination of the metrics. The challenge is that if you actually try to align a group of people or even a single business leader on what the right weights are, it's hard to get them to choose weights, right? They're really nervous about it. They don't know what they should be. A second approach is multi-objective optimization, multi-objective Bayesian optimization. And this works pretty well in the setting where we have only let's say 2 metrics. So in this context, what we do is we create an estimate of a Pareto frontier. The Pareto frontier is the collection of solutions that are non-dominated, such that, so for example, this point B is non-dominated because if I want to make the revenue better, so if I want to increase the revenue, the only way to do that is by decreasing the price. So there are no other points that dominate it, while this gray circle, you can both increase its revenue and its profit by going up to B. So the idea in multi-objective Bayesian optimization is I estimate this Pareto frontier, then I show the Pareto frontier to the decision maker and ask her to select a point on that frontier. The problem is that if you have panels of metrics that have more than two or three metrics on them, then you need a really large number of experiments in order to estimate the Pareto frontier. Often, almost the entire search space is on the Pareto frontier. So the motivation that I'm going to propose comes from working at Uber and working with specific decision makers at Uber. So to make this concrete, I'm going to show you Margaret Tian. Has since left Uber and now works at a generative AI startup. But I worked with her very closely for a long time. And by working with her and by meeting with her and understanding how she thinks, I can often predict which panel of metrics she's going to prefer out of all the panels of metrics that I might be able to create by changing parameters in, let's say, the matching algorithm or another algorithm. So from this experience, our hypothesis in this work is that a decision maker has a utility function over panels of metrics, or in the case of generative AI, over AI-generated content. The problem is that they struggle to articulate it. You can't get them to write down a mathematical function that's inside of their brain. So the approach that we're going to take in this work has 2 steps. The first is preference exploration. We're going to ask the decision maker a collection of questions in order to learn something about their utility function. And this is actually going to borrow on old ideas from the literature on utility elicitation, and also is a nice springboard on which we can move towards using more modern methods as well. So that's the first step, preference exploration. From that, we'll get some partial information about what the decision maker's utility function is. Thinking in a Bayesian way, we'll get a posterior probability distribution over utility functions. And then we can use that to choose A/B experiments or AI model hyperparameters to run. In order to implement the solution, we have to make a bunch of decisions. So when we do preference exploration, and in this work, we're gonna think about asking questions that are of the form, hey, between panel Y and Y prime, which one do you prefer? Right. So these are called pairwise comparisons, and they have a long history of producing high quality data for understanding preferences. The second question that we're going to ask is, when we're about to perform an A/B test, which experiment X should I run? In order to support these design decisions, we're going to build Bayesian surrogates via Gaussian process regression for the forward model. So this is the model that maps a, a parameter vector X onto a panel of metrics Y. And then also the user utility function, which maps a panel of metrics Y onto their utility. And you see that shown over here. So in preference exploration, I'm selecting a pair Y and Y prime to present to the decision maker, getting a response of which one they prefer. Then in A/B testing, I'm selecting an X at which to observe the panel of metrics. Then I'm going back to preference exploration, and I'm iterating many times until finally at the end, I present the decision maker with all of the panels of metrics that we've been able to generate using A/B testing. And she selects the one with the largest utility among those tested, where only she knows this utility function and can't articulate it to us mathematically. Feel free to stop and ask questions. I'll try to keep an eye on the Zoom chat or raise your hand. And then also, I'm sure the organizers will be able to let me know if there's a question to answer. So we're building on a few different lines of work. Certainly multi-objective Bayesian optimization that I talked about previously. There's also a line of work on preferential Bayesian optimization, which assumes that each parameter vector X directly, that you can take pairs of X's and present the X's to a decision maker and ask for their preference. So the relationship between what we're doing and that is that we're also assuming visibility into this kind of intermediate outcome Y of X, which is generated, and we'll derive a lot of extra kind of query efficiency from that approach. Also using lots of technologies from kind of older work in machine learning and econometrics on preference learning and utility elicitation. And then also what we're doing is also, quite related to reinforcement learning with human feedback and the closely related area of preference-based reinforcement learning. Okay, so what we're doing is really like adaptive experimentation, AI-based experimentation. And in these approaches, there's kind of two components. One is inference, and the other one is experimental design. So if we're doing inference, we're borrowing kind of existing technologies. For A/B testing, we are modeling the relationship between this decision X and some outcome vector, some panel of metrics Y of X using multi-output Gaussian process. And then for user utility, we're also using a GP-based classification method that assumes that users choose between panels Y and Y prime according to, oh, and there's a typo here. It should be the difference in utility functions. So the logistic function of U of Y minus U of Y prime divided by some scaling parameter lambda. So if a user prefers, if the utility for Y is higher than the utility for Y prime, they're more likely to say that they prefer Y. Okay, so inference, pretty straightforward. How do we do experimental design? So first, A/B testing. And I just want to remind folks about some background from classical Bayesian optimization in the single objective case, and specifically the decision theoretic motivation behind expected improvement. So in expected improvement, we've evaluated just a single objective function n times at these points, x1 through xn, and we've observed the function values, let's say without noise. So the best value that we've observed so far is f star, which is just the maximum of the observed values. If we evaluate the objective function at a new point x, we're going to observe f of x. So the new best value observed is going to be the maximum of the old one and the new value. The acquisition function, called expected improvement, is defined by this quantity here. So it's the expected value of the quality of what we'll have after we do this evaluation at x minus the value of the best evaluation before we evaluate it at X. Okay, so it's really this like difference in expected quality of the best before and after evaluation. So let's take that same analysis approach and apply it to the setting where we don't know what the objective function is, but where a decision maker is able to select from a collection of options according to that utility function. So what we're trying to do is preference exploration and A/B testing in order to maximize this quantity. We're trying to put together a panel of solutions that we have generated, capital N solutions, capital N panels of metrics, such that when the decision maker looks at them and evaluates her utility function for all of them, right? So calculates kind of this quantity in their head, and then chooses the one for which this utility is the largest, right? So that's this maximum. We want to design these XIs so that in expectation over the utility function, the expected utility is really high. Okay? And this expectation is over both, I guess, the unknown utility function and any randomness in the panels of metrics that exist because we're modeling them in a Bayesian way and we don't know what they are. So with that understanding, let's apply the expected improvement kind of way of thinking about the world, right? So let's say that we've evaluated N panels of metrics, and we're not going to do any more experiments, and the decision maker is going to select the one that's the best for their utility function. So the value that they're going to get is just this quantity here. Unlike in the classical expected improvement case, we don't know what U is. And so because of that, we don't know what this U star of N is. But that's okay. Now, let's say that the decision maker, we're going to add one more panel of metrics into the collection that we've evaluated using A/B testing, and the user is going to be able to select from this largest set. Then the value that they get in that setting is this U star of N plus 1. And it's just the maximum over this larger set of evaluations of the utilities. And you can write it as the maximum of the old best and the utility of the new option. The acquisition function that we use in this work is defined by taking the difference in those values, so that U star N plus 1 minus U star N, right? So that's the improvement in user utility that results from adding one more panel of metrics to the set. This is random, both because we don't know when we make this decision of which X at which to run our A/B test. We don't know what Y of X will result, and it's also random because we don't know the user's utility function U. So we take the expectation over both of those sources of randomness indicated by this expectation here. And this is what we call the expected improvement with utility uncertainty, or EIUU. You can also write it like this, and it looks very similar to the expected improvement, except that this U is random. I'll also mention that I use this notation both here and later in the talk. So E with a subscript N and subscript M. So N is the number of A/B tests that I've performed, and M is the number of user queries. And through performing A/B tests and user queries are just asking somebody which they prefer between Y and Y prime. I'm updating my posterior distribution on the mapping from X to Y through A/B tests, and on the utility function through user queries. How do we actually optimize that? We rely on what's called sample average approximation, for which Blowtorch has infrastructure that makes it really easy to implement. In detail, what we do is we sample utility functions from the posterior. And since we're using a Gaussian process, an approximate Gaussian process posterior on the utility functions, is really taking samples of functions from Gaussian processes. And then uh, also sampling values for normal random variables, multivariate normal random vectors that we can use to simulate the randomness in the panel of metrics Y. Okay, and so this expression here, uh, you can, uh, the expectation of this expression with the positive part is equal to the EIUU using the reparameterization trick if you're familiar sort of with this area. And so when the number of samples J and K is large, this expression converges to the expected improvement with utility uncertainty that I just showed you. And also it's a continuous function in X if you hold fixed the samples Zj and U star of K, and if these samples are continuous in their arguments, or I guess UK. Uh, and so then you can optimize it using using a classical optimization method. And so that's what's implemented in BoTorch. Just some illustrative numerical experiments on some simulated problems looking only at the A/B testing portion of this pipeline, where we're holding fixed some posterior distribution over the user's utility function, and then we're increasing the number of times that we can evaluate this y of x and looking at the expected utility of the best solution found. And we find that among a collection of approaches for choosing which A/B experiments to run, the acquisition function that I just showed you, which is this blue and also the cyan version, outperform competing methods. But let me talk about how we do preference exploration, because that's kind of an equally important part of the story. So just to remember, what we're doing is we're trying to find solutions that the user finds attractive by iterating preference exploration, where we ask them questions about what they want, and A/B testing, where we find out through A/B testing what's possible in the world. So our approach, our goal in preference exploration is really to choose queries that identify feasible outcomes, so feasible from the perspective of A/B testing, that have high utility. The approach is we're going to fit the user's utility function, as I explained previously, using kind of a standard Gaussian process classification, to the decision maker response data, where I've presented them with pairs of panels of metrics and ask which one they prefer. And then we're going to choose pairs y and y prime via a novel acquisition function. This acquisition function is called the expected utility of the best option. I'll define in just a moment. So kind of like, here's a way to think about the problem that we're trying to solve. So I have, let's say I'm trying to do preference exploration for a setting where there's two outcomes, right? And I don't know the user's utility function over these two outcomes. Maybe this is profit on the x-axis, and maybe this is revenue on the y-axis. Here I'm showing in kind of the red shading, I'm showing the user's utility function over those pairs. And then because I don't know what's possible, because I haven't run an infinite number of A/B tests, I don't know what the feasible region is. I don't know what this set is. So this is the set of all capital Y of X, where X is moving over the space of possible decisions. And I'm showing you samples from that posterior distribution through these different contours, right? So maybe one sample is this shaded dark gray line, another one is this dashed gray line, another one is this dashed white line, dashed black line. And so what we're really trying to do is to figure out, hey, among those points that are likely to be feasible, which ones have high utility? So one way to tackle this problem is using a decision theoretic approach with a one-step, kind of a one-step motivation, similar to how we thought about expected improvement previously, right? So, and I've written that out here in excruciating detail, where I have a pair of metric panels Y1 and Y2 that I might present to the decision maker in order to assess her preference over them. And so what would be the value of asking this one question and then doing one more A/B test and getting the result and then choosing from among the set of solutions generated the one that we think has highest utility for the decision maker. So that's what defines this quantity W. And the idea is that that would be a reasonable acquisition function over pairs Y1 and Y2. You can parse this out. So this is the expectation over both the user response and the result from the A/B test. So then based on the result from the A/B test, I'm going to choose a single additional A/B test to run. Then I'm going to take the expectation over the maximum over all of the solutions that I will have generated, including this new one. I'll take the maximum of the expectation of the user utility. Okay, and so ideally we would calculate W and then optimize over it. The problem is it's really hard to compute and optimize over. Fortunately, there's a much simpler quantity that such that when you optimize over it, you get an optimal solution to this one-step look ahead, or maybe you could think about it as a two-step look ahead kind of acquisition function. And that's this UBO, or expected utility of the best option, which is defined just by taking the expectation under our current posterior of the maximum of the utilities of the two panels of metrics that I'm thinking about asking the user to compare between. And this is something that's much easier to optimize over. How do we do that? Again, we use sample average approximation and the reparameterization trick, where when we optimize over the pair of panels of metrics Y and Y prime, we optimize over a sample of the feasible region. That's this like mathcal Y hat, and then we use samples to define an estimate of the UBO for a particular Y, Y1 and Y2. Okay, and again, some illustrative numerical results on some synthetic problems using this iterative preference exploration and E/B testing approach to optimize over the design of a car cab in a crash test, where this black line is the true utility. If you knew the true utility function and could use standard Bayesian optimization, then you could achieve a high utility really quickly. But if instead you use our approach, so expected utility of the best option, you more rapidly compared to benchmarks with the same access to information about user preferences, we're able to increase user utility through batches of preference exploration and A/B testing. So those are some synthetic problems, but let me tell you about how this was used at Meta to generate value. And talk about two different things lining up with the motivation that I introduced at the beginning of the talk. So the first is exactly, it was used at Instagram to decide on algorithm parameters to drive product changes where the decision maker was a product manager at Meta, and the product manager used this interface in order to express preferences over panels of metrics. So the way that this works is you have 5 different metrics here. So I'm not showing you exactly the names of these metrics for confidentiality reasons. And the product manager was asked to compare a blue panel of metrics with a yellow panel of metrics. So these panels of metrics are presented not as points, but as confidence intervals, because that's typically the way that A/B tests produce results. And so the product manager is presented with this and then asked, hey, between these two panels of metrics, which one do you prefer, the yellow one or the blue one, the top one or the bottom one? And then the second way that this was deployed at Meta is for automatic video dubbing. So Mark Zuckerberg will explain this in just a moment. But what you'll see is a generative AI pipeline that is designed to take in a Spanish language Instagram reel and translate the audio into English, and then also take video of any speaker's mouths and change the pixels in the video so that it looks like those speakers are speaking English instead of speaking Spanish. Okay, and so this is a generative AI pipeline that has more than just a single kind of AI model that's doing video translation and doing audio translation. It has a bunch of different components that are glued together. And these components are glued together with hyperparameters. And so the algorithm that I just described was used to tune these hyperparameters.
With automatic video dubbing on Reels, starting with English and Spanish. So this is going to be a way that you can see more of the content that's out there, no matter what language you speak. And as a creator, this is going to let you reach a lot more people around the world, no matter what language you speak. So now you're going to be able to take your content, and it's going to be in your authentic voice, speaking other languages if you want. And we're also doing automatic lip syncing, so that way it actually looks like you are speaking the other language. So let's check this one out.
De coco, banana y dulce de leche. Esta receta fue una de las primeras que subí a las redes. Hace poquito la volví a descubrir y le hice un par de modificaciones para que sea aún más deliciosa. With coconut, banana, and dulce de leche. This recipe was one of the first ones I uploaded to social media. A little while ago, I rediscovered it and made a couple of modifications to make it even more delicious.
With automatic video.
We're generalizing this approach in a few different ways, and in closing, let me just describe one of these generalizations that I'm really excited about. So there's two components to what I'm talking about. One is the user interaction, and the other one is the A/B testing, and we can generalize both of them. So in the user interaction, there are lots of ways to interact with people to understand their preferences, right? So presenting pairs of options and asking which one they prefer is one way. Another way, pretty natural in the world now where LLMs are so easy to use, is through natural language. And then a second approach is through user configurable filters and ranking, like the kind that people use on Google Flights or Kayak in order to explore different itineraries, airline itineraries that you might purchase. So you can generalize the user interactions in all of those ways and other ways. The second component that you can think about generalizing is the A/B test, right? So that's one way to understand the relationship between X and Y of X, right? Is a zeroth order oracle. You pass in an X and it returns to you Y of X. A different kind of interaction that shows up a lot in operations research, the kind of academic discipline from which I come, is you pass in a utility function U, and you get a solution to the single objective maximization problem. So you get an X star that maximizes U of Y of X. We're applying one context where we're applying a generalization based around these ideas is in scheduling final exams at Cornell. So this is a multi-objective decision-making problem where you want to choose an exam schedule, so an assignment of classes to time slots for final exams in order to, on the one hand, minimize the number of exam conflicts, but also to ensure that students can leave campus quickly so that students don't have to stay around on campus forever, and also to ensure that students have sufficient time to study in between exams, and also to make sure that we have enough rooms to be able to give large exams, like a single dedicated room, so that instructors don't have to go back and forth and proctor exams in two rooms simultaneously. So it's a multi-objective problem where the registrar and other stakeholders have preferences over panels of metrics, right? So the panel of metrics is like the number of direct exam conflicts, the number of exams that happen, student exams that happen one right after the other, the number of times that students have two exams on the same day, even though they're not back to back, etc. So for user interaction, we are moving towards using filtering and ranking interfaces like on Google Flights. And then our forward model uses a mixed integer linear program where you enter a linear utility function u, and you get an x star that maximizes u of y of x, where x here is a schedule. It's a big, huge CSV file that has an assignment of classes to exam slots. I should mention also that this is joint with a number of people here at Cornell, including David Schmoys and quite a few students. Here's some kind of preliminary results from applying these kinds of ideas to a different scheduling problem, which is scheduling patients with doctors. And we're able to show that as you increase the number of interactions with the decision maker, where you can present in these simulations pairwise comparisons, the utility of the best solution that we're able to produce rises. And we're looking at a variety of different methods for both supporting those decision maker interactions and then also for interacting with the forward model. And we have both an optimal, a kind of an optimal approach in one particular sense, and then also methods that are suboptimal and that are significantly faster without losing too much performance. Through this work, really what we're trying to do is to increase access to optimization as a methodology, right? So if you've used optimization in an application today, then the way it works isn't that great. Like a company has a problem that they think optimization could solve, and then they spend a lot of money, tens of thousands of dollars, hundreds of thousands of dollars to hire experts to work with them on that problem. And then it takes, at least 6 months, maybe years before you get an optimization model that's in production and actually making decisions. The way that it should work is that, an everyday person has an optimization task, and it happens all the time, right? You need to go to the grocery store and buy groceries for your kids. You need to make financial decisions. You need to figure out carpool. So we're trying to drive towards AI systems that can interact with people and can understand what their preferences are, and help them have access to optimization without having to pay an expert. So just in conclusion, we provide here a novel framework for multi-objective optimization with expensive forward models, where the key idea is to model the decision maker as having an unknown utility function. We propose novel strategies for zeroth order oracles. That was the focus of the talk. And then ongoing work with mixed integer linear programs. And really what I'm hoping to do in this talk is to excite people that there's a lot of interesting work to be done at the interface between preference exploration and optimization. So let me stop there and thank everybody, and happy to take some questions. And maybe I can start with this question from Sarah, which is a really good question. How do we incorporate the feedback from multiple stakeholders? Does each one get their own utility model? Does one inform another? How do you find the optimal compromise? Yeah. So this is wide open. It's both really important because most really critical problems are multi-stakeholder problems, and there are no AI solutions for it. I've been thinking about it as the goal in a multi-stakeholder problem is to find a consensus, find a solution that people can all tolerate. And the way to do that, yes, is to I think a good starting point would be to develop utility models for each person individually, and then to understand, a simple approach would be to, okay, let's then search for solutions such that all of the people have, near optimal utility. And if you can find one, that's definitely a consensus. And if you fail to find one, then I think one needs to, at that point, understand the levers that the stakeholders can pull in terms of, influencing each other, and probably requires a little bit more modeling. Yeah, that's an exciting direction. I think it's super cool.
Sorry. I would just like to briefly mention a little bit about the format for the question and answer, which is that we're going to have two question and answer periods. The first of those is going to be live streamed on our website. And then following that, we will disable the live stream. So anybody who's kind of not comfortable with asking questions that get broadcast live on YouTube, feel free to stick around a little bit, and we'll also have some time for you to have an opportunity. And on that note, I'll hand back to Peter.
Okay, and then Z asked an excellent question. What's your view on the principles for learning utility functions from natural language feedback from users? Um, Again, yeah, and I think there's a lot to be done here. Um, we are working on an approach where you provide as a prompt to an LLM a history of natural language interactions with the decision maker, and then ask uh, to make predictions over pairwise comparisons, right? So it's like, hey, I'm trying to I'm trying to design a custom running shoe for this person, right? And I presented the user with maybe two different running shoes and asked them to run in them and said, "Hey, how do you feel? You know, tell me which one you prefer, and then also tell me a little bit about why," right? And they're like, "Oh, I prefer this shoe." And why is it? "Oh, it's because my toes get pinched in this other one," right? And so you provide my toes get pinched in, whatever the such and such shoe to uh, to a system, and then you ask the system, okay, so now here's two more running shoes, and here's like a panel of metrics describing those two running shoes. Which one do you think they would prefer, right? And so you can generate a bunch of synthetic pairwise comparisons from these kinds of interactions and then fit sort of standard models. So that's one way that we're hoping to go. Another way that we're hoping to go is just to drop the whole utility modeling thing and do more of a kind of a model-free kind of neural architecture that takes as input um, uh, just a history of interaction and then produces directly a pair of items to present to this, or that presents some kind of like um, what the form of whatever interaction we want to have with the user next. And so in order to do that, you need a way to generate synthetic examples to train that system on. So those are two approaches that we're going down. But yeah, I think that's a super interesting area. Yeah, can I comment on potential limitations with the MILT model? For instance, you won't be able to access the full Pareto frontier. Yeah, I think so. One limitation of the MILT model is that MILPs only optimize linear functions. So if the decision maker's utility function is nonlinear, then right, you're not going to be able to, like if the Pareto frontier is non-convex, then like you're saying, you're not going to be able to get like inside that non-convex. Probably my drawing with my hands is not helping, but if you have a non-convex Pareto frontier, then linear functions are only able to access the convex hull of it, and so you're not going to be able to get inside. So that's a limitation. Um, we're thinking about some analysis that gets around some of that limitation by really what you wanted in the case where you have a user with a nonlinear utility function and a convex Pareto frontier. It's enough to estimate, and you're required to use linear approximations to the utility function. It's enough to estimate the like first order Taylor approximation of the utility function in the neighborhood of whatever the optimal solution is. So we've been like trying to figure out algorithms that have the property that they like converge, they're kind of converging to wherever the optimal solution is, and then making sure that they get the right first order derivative. Um, yeah, so that's definitely a limitation. Good question. Anything else that I can answer for people.
So I think perhaps it's not a bad time to conclude the YouTube live stream just based on time. So I wanted just as a final announcement to say that we have more seminars coming up. You can find them at gp-seminar-series.github.io, where you'll have instructions to sign up on the mailing list and everything else. And I wanted to say thanks so much for all of our YouTube viewers to join us, as well as to my co-organizers, uh, Z Wang, Renato Berlingeri, and Natalie Mouse, for helping put this together. And we'll see everybody, I believe.